Have you ever wondered how a boat can sail against the wind? Or how a massive bridge can just stand there totally solid against all these competing forces? I mean, it seems impossibly complex, right? But the answer, well, it's actually in a simple, really elegant shape. Today, we're going to unlock the secret of the parallelogram law of forces. It's this awesome visual tool that helps us make sense of the whole push and pull world all around us. All right, let's dive right into this with something we can all picture. So, imagine you're trying to move a heavy box across the floor. Easy enough, right? It's just a simple push and pull. But what happens when things get just a little bit more complicated? So let's say you're pushing that box straight ahead, but then your friend comes along and decides to help by pushing from the side at the exact same time. Where does the box actually go? Does it go your way, your friend's way, or does it kind of carve its own path somewhere in the middle? You know, our gut feeling gets us part of the way there, but physics gives us the exact answer.
And this is the brilliant part. The tool we use to predict that path, it isn't some supercomputer or a crazy complex equation. No, it's just simple geometry. A shape you probably learned about back in grade school is the key to figuring out exactly where that box, or really any object, is going to go next.
So this powerful principle, it has a name: the parallelogram law of forces. It's a really fundamental concept in mechanics, and believe me, once you get this shape, you are going to start seeing it absolutely everywhere. Okay, I know, that sounds a little formal, kind of like something out of a textbook, but let's just break it down. It's simple. You have two forces, right? Just think of them as the two sides of a parallelogram that touch. Their combined effect, what actually happens, is just the diagonal of that shape. That's it. We're basically trading two separate pushes for one single, true path, and the shape itself just hands us the answer. Yeah, let's just cut through all the jargon. The easiest way to think about this is as a visual shortcut. Instead of getting all tangled up trying to figure out two different forces, this thing literally draws you a map to the one true path the object is going to take. Okay, so how do we actually use this map? How do we build this solution? Let's do it. Let's walk through it together and solve our little box problem once and for all. It's just a simple three-step process. You'll see. All right, here we go. 3 simple steps. Step 1, you draw your two forces. Just represent each one as an arrow, we call them vectors, and make sure they start from the very same point. Step 2, you complete the shape. You just draw lines that are parallel to your original arrows to form a perfect parallelogram. And then step 3, the big reveal. The diagonal that you draw from that starting point, that is the true path. That single line tells you everything: the final direction and the combined strength of both forces. Pretty cool, right? Okay, so this is great for figuring out where a box is going to slide across a room. But why does this one little law matter so much in the real world? Well, it's because it scales up. Way up. We're talking from tiny, tiny particles to the most massive structures you can imagine. This simple geometric shape, it's like the hidden architecture that's holding our world together. I mean, think about who uses this. It's a cornerstone for so many different fields. Structural engineers, they totally depend on it to figure out how all the forces, weight, tension, compression, are spread out through a bridge. An airplane pilot, they're using it to calculate their true course when a big crosswind is trying to push them off track. And what's really cool is how versatile it is. Even video game physicists use it to make sure that when you throw something in a game, it actually flies through the air in a way that feels real. And look, we're not just talking about doing this calculation once. For just a single complex part of a bridge, like a truss, engineers might have to solve for this resultant force hundreds of times. They're analyzing every single joint, every single beam, to make absolutely sure all those competing forces balance out safely. It's the invisible math that literally keeps us safe every single day. So, what's the big picture here? What are we really talking about? The parallelogram law, it's not just some tool for engineers. It's like a new lens for your eyes. It's a way to see the hidden geometry that's governing motion all around us. And this quote just captures that idea perfectly. We tend to think of forces as these invisible pushes and pulls, right? But geometry gives us a language to actually see them, to describe them, and most importantly, to predict what they're going to do. It's like the universe is speaking to us in shapes. So if there's one single thing you take away from all this, let it be this. What might look like total chaos, a flag flapping in the wind, a ball bouncing off at some weird angle, It's actually this beautiful, intricate dance of forces. And it's a dance that follows clear, predictable geometric rules. This law, it's our ticket to understanding the choreography. So I'm going to leave you with this thought. Right now, wherever you are, countless forces are at play. You've got gravity, the pressure of the air, the support from your chair or the floor. Now that you know the rule, can you start to actually visualize those hidden parallelograms all around you? What unseen forces are shaping your world right now?